lightning and electromagnetic interference or lightning protection. This is module number 6.2. In this we will look at properties of lightning which has influence on protection. We will concentrate on currents and charges from lightning flash and the electromagnetic fields. So, these are the two quantities that affects earthbound systems. What is shown here is an overall sketch of vertical electric field wave shape of a typical ground flash at a distance of a couple of kilometers. So, this is from the lightning channel. These fields are produced by the lightning channel, the vertical part from connecting earth to the cloud. Now, if you look at the portion over here, so as lightning is coming down from the sky, first it is in the form of a leader that you will not be able to see with the naked eye. As it is approaching the ground, it will create a electric field change that goes in one particular direction. So, here it is negative, this is a negative leader. So, we are talking of negative cloud to ground flashes. Now, the time scale is this much is about 100 milliseconds. So, we are talking of about several millisecond process. The speed of the leader may be of the order of 10 to the power of 5 to 10 to the power of 6 meters per second. Then once it comes very close to the ground, there will be upward leaders going from objects on the ground which will connect with this downward leader, and you get a return stroke which is a very fast rising current. Associated with that you hear the bright flash and thunder. So, that process is shown over here. So, this is how the electric field change will look like during a return stroke. So, the rise time here is just a few microseconds only. So, from millisecond scale, this process they are in microsecond scale. The vertical scale is around 200 volts per meter if you take this much distance, and this is a couple of kilometers away from the channel, and the return stroke reaches the cloud, then travels horizontally neutralizing several charges, and the channel to the ground become kind of extinguished in the sense that there may be still a plasma channel, but you will not be able to see it. It is not bright anymore. So, it is a dark period, and during that time there will be rearrangement of charges in the cloud that will manifest in the electric field as step like changes, and they are called K changes. Then after that, along the previous channel there may be another leader coming down, and these leaders are called dart leaders or subsequent leaders, and again a millisecond scale. Then as it is approaching the ground, you will have another return stroke, and that return stroke is shown here, the second stroke in microsecond scale. Then after that again you have a dark period. Then along the channel a third stroke. Well, obviously this stroke is very small stroke from the magnitude you can see. Then following that, in this particular case you will see a continuous luminosity of the channel, and that luminosity is represented in the electric field by a slowly varying electric field. So, this is the continuing current phase. It means that the return strokes are of the order of few thousands of amperes, whereas during this continuous current which lasts several few hundred up to few hundred millisecond, the currents are of the order of maybe less than 1000 ampere or few hundreds of ampere only, but that will give a glow to the channel, and during that period you will have again several pulses coming down the same channel, which are called M components, and that are shown here. These are not return stroke, but slow varying pulses. Then you have a dark period over here, then again a fourth stroke, then again a fifth stroke, then some rearrangement of charges in the cloud, then finally the flash get extinguished. The whole process is less than 1 second. So this is a pictorial representation of an actually measured lightning flash in Florida in the 1970s. So this gives several processes in the lightning flash, and of that, as far as interaction with systems on the ground is concerned, we are mostly concerned about the return stroke, that is the most energetic thing, and we are also concerned by this continuous current also, because even though it carries only hundreds of amperes, it because of the long time it produces a lot of charge, and we will see that a lot of charge means that fire hazard to the objects and other things. So the return strokes and the continuing current are most important as far as lightning protection is concerned, and the leaders are important because it is these leaders that will finally decide where the lightning will strike. So there is an empirical formula between the charge in the leader as it is coming down and the peak current in the return stroke. So this peak current in the return stroke will decide at what distance the lightning will decide where it will strike. So the last 40 or 50 meters or even 100 meter distance from the tip of the leader to the striking object is very crucial, because it is during that time the upward leaders will be initiated from the grounded objects, and it will be decided where lightning will be striking. So this has got an influence in the protection also. We will see that in a later module. Now, previously we have seen the process of triggered lightning by shooting a small rocket upward with a trailing wire, and lightning can be artificially triggered with those type of technique from thunderclouds. So what is shown here is a current that is measured at the base of the channel, actual lightning current during one of those triggered lightning, and here if you look at the scale, here it is in millisecond, up to 1 second is shown, the current is in amperes, up to 2000 amperes are shown. Now these pulses 1, 2, 3, 4 like that, most of them are above 2000 amperes, but it is kind of cut to show the finer details of low currents. What you see here is the initial continuous current process of few hundreds of ampere in amplitude. This is the so-called stage immediately after the wire burn, where there is a continuous current. This part is only present in upward initiated lightning or in triggered lightning. It is not there in natural lightning. So, your first stroke is kind of replaced by this initial continuous current, but remaining parts of lightning is very much similar to natural lightning. So, first stroke, second stroke, third stroke, so up to 9 strokes are there, and you have some continuous current, and time interval are several milliseconds, and here it is little more than 100 milliseconds, and M components, the slow varying pulse superimposed on the continuous current. So, when an object is struck by lightning, then all this kind of environment is present. So, the object is subjected to not just one lightning pulse, but several pulses within the flash, separated by few tens to few hundreds of millisecond. So, that is the lightning strike environment, and associated with that you will have strong electric and magnetic fields. Now, in this picture some measurements done in Uppsala, Sweden in 1995 are shown. So, the top picture shows overall wave shape, electric field change wave shape from lightning during a thunderstorm, and the middle graph shows the current measured in the power outlet between one of the wires and the ground, the earth conductor. So, it is like a common mode current, common mode voltage, actually it is voltage, common mode voltage of a wooden building that is completely isolated from external power lines. So, it is like a huge object, a building with its normal electrical wiring, piping and everything. So, what is tried here is to see what effect lightning will have on a structure. So, the voltage is measured in one of the power outlets between one of the two lines and the earth. Now, these are the actual voltages, and this lightning was about 20 kilometer away. And first let us describe this electric field diagram. So, what is mentioned as P here are very narrow pulses that happens in the cloud. It is not happening in the ground or in the channel to the ground. So, the leader is not yet initiated here. So, these are just breakdown process within the cloud, that is maybe several tens of kilometer away from the building. Then already the building is responding to those events in the cloud. So, the structures can respond not only to the events that happens in the lightning flash channel to the ground, but even those events that happens within the cloud even before the channel is formed. So, you can see all this induced voltage pulses up to 80 volts, and in this bottom graph how many pulses above certain value are counted, certain threshold value. So, here bottom window shows histogram of induced common mode voltages exceeding 80 volt peak to peak. Say for example, this is 40 and this is 40. So, 80 volt peak to peak. So, how many pulses are exceeding that value? So, already at around 7 millisecond you have 12 pulses that exceed 80 volt peak to peak has occurred. So, likewise you can follow how intensively induced voltages are there from this graph, and this shows the actual wave shape of the induced voltages on a millisecond scale for finding the details, one has to find it in a microsecond scale. And this is the first return stroke. Then after that, again you have some quiet period and some events in the cloud. Again, the structure is responding to that, producing pulses. Then the second return stroke, third return stroke, they are very small return strokes. Then some pulses in the cloud. Then what is shown here is a cloud flash. It has no connections to the ground. This happens in the cloud only. So what is interesting is that even though all these pulses, bipolar pulses, are happening in the cloud, the structure is responding to this, and you can find how many pulses exceeded 80 volt peak to peak over here. So the conclusion from this is that any lightning that happens, whether it is cloud to ground or cloud to cloud, the structure is responding. But usually it is cloud to ground lightning that is more of a threat, because this is now more than 20 kilometer away, but it can be just a few kilometer away from the structure. Then of course, these peaks, return stroke peaks, will be quite dominant in inducing the voltages in the structure, and that will have extremely high values compared to that happens in the cloud. So, if you look at a lightning flash, there are many events that happens in a lightning flash, and all of them has got some effects on the structures. For example, we are not looking into the properties of all of this. We will only look at some properties of return stroke and continuing current only. But there are many events in lightning flash that will produce electric and magnetic fields, induced voltage effects, VHF radiation, etc., whereas return stroke can directly strike objects and produce large currents, charges, not only the fields. So this becomes most important for our study, the return strokes. And M components also to some extent, because that also a continuing current and M components goes together. So this also can have direct effects. For other events, it is mostly electromagnetic fields. The waveform of a lightning return stroke current measured at the base of a channel is given. From around 1 second, this shows only 50 microsecond. So 1 by 50th of a million, you can say, of length of a record. And in this particular return stroke, it has got 16 kiloampere, 16,000 ampere peak current, and 10 to 90% rise time, that is from 10% of the peak value to 90% of the peak value, it will be 0.36 microsecond. So 10% and 90% are taken to remove some of this uncertainty at these junctions. And the range of peak currents for return strokes are anywhere from 2 kiloampere to 200 kiloampere, and average speed of the return stroke pulse propagation from ground to cloud is 1 to 2 into 10 to the power of 8 meters per second. So 1/3 to 2/3 the speed of light, and typical maximum current rate of rise is 100 kiloampere per microsecond. So we are very much interested in this figure in terms of peak current, because current squared time any resistance, you get the effect that is happening in terms of the power. And here di by dt, of course you can translate it into induced voltages in relation to inductance. and this is the channel radius and channel temperature. Of course, this is important in terms of melting of the object where lightning is striking. So, the properties of current parameters in cloud to ground lightning is summarized here. So, you can use this for reference. What is shown here is the typical value or some sort of an average value, and what is shown here is the extreme value, that is maximum value that people have measured with real lightning. For example, number of return stroke in a flash, typically a flash contains several return strokes. So, typically it is 4 to 5, whereas extreme value can be 26. Peak current in negative cloud to ground lightning, then peak current derivatives, impulse charge transfer, that is during the return stroke how much charge. If you integrate the waveform of the return stroke, say for example, if you are, this is a return stroke. So, if you integrate this area, so this is in time and this is in ampere. So, if you integrate this area, that will give you the charge. So, impulse charge and prospective stroke energy. So, if you take I squared in each of this area, I squared, charge squared, current squared, then delta t, then if you sum up all those things, then you get prospective stroke energy. So, this is for the first return stroke, this is for subsequent return stroke that follows the first return stroke. So, which are a little lesser in value. Then positive return stroke, this is from positive cloud to ground lightning, where you have much more higher amplitudes in the extreme cases. Then continuous current and total flash charge. So, these are important engineering parameters that are required in designing lightning protection systems. Electric field parameters from cloud to ground lightning. So, fields, we will consider 3 distances. One is fields close to lightning, 0 to 500 meter, let us say, that is half a kilometer. Then fields far away, that is several kilometer away. Then some intermediate distance, 500 meter to a few kilometer. The reason for doing is that if you have the lightning channel here, and if you look at the fields, if you measure the fields at various distances, the vertical fields E, it follows a certain relationship as a function of distance d, and close to the channel and far away channel, E is proportional to 1 over d, peak field, E peak is proportional to 1 over d. So, here you can say that E peak is proportional to 1 over d approximately, and here also E p is proportional to 1 over d, but here it is not like that. Intermediate distance that comes from the peculiar combination of the geometry and the various processes in the channel that give rise to the field. So, let us look at the details. So, electric field very close to the lightning channel, a picture is shown here. So, you have the leader that is coming down And now here this is in microsecond scale, because you are so close to the channel, it is only a distance of 50 meter. So, this is the last several meters that you are seeing. Then you have the return stroke. So, this follows a very narrow bipolar pulse. This wave shape is also very different. Say up to 0 to 500 meter, often you have leader and return stroke of this form. This is a leader and this is a return stroke R. Whereas at intermediate distance it may be something like this, and far distance you will find only something like this. So, this is the return stroke and this is the leader return stroke. So, even the wave shapes are different. So, we are mostly interested in this return stroke part. So, this narrow bipolar, the narrow bidirectional or narrow pulse is formed only when you are very close to the lightning. So, even before the lightning is striking, your structure will start responding to the leader fields. Now, the electromagnetic field environment from close lightning are described here. E dE by dt, H dH by dt. The typical values and expected maximum values are given, and at various distances from 10, 50, 100, 500. So, these are based on measured data, and extrapolation of measured data is done here. Say for example, at 50 or 100 you have around 30, 60, 50 like that. So, peak fields falls off approximately inversely proportional to distance, that is peak field is proportional to 1 over r, where r is the distance. Say for example, electric field at 80 meter, then you will determine like, okay, you have it at 50 meter 60. So, 60 into 50 by 80 because of this proportion. So, 37.5 kV per meter. So, likewise you can determine the field peaks, and this is approximate, each lightning is different. The above field values can be used in the estimation of induced surge or voltage currents in electrical circuits of the system due to indirect lightning strikes. Now, electric field peaks at far distance. Field peak at intermediate distance does not obey the 1 by r relationship, and it may have a greater fall off rate, whereas field peak far away is dominated by radiation fields and falls off as 1 over r. Now, typical return stroke field peaks in negative cloud to ground flash normalized to 100 kilometer distance. For the first return stroke peak field, it is given by the value 8.6 volts per meter or around that value, and for subsequent return stroke peak it is around half that value, 4.3 volts per meter. So, since it obey roughly 1 over r relationship far away, say typical fields at 10 kilometer distance, you can find it to be 86 volts per meter first peak and 43 volts per meter subsequent peak. Now, what are the effects of lightning, electric fields and magnetic fields? Say electric fields are vertical. So, it means that electric field times distance will give you the volt. So, if you have a metallic structure that is above the ground, the structure will go up in potential by an amount of h times EV. Say this is one kind of an effect. So, if you have different structures, so this different structures may be at different potentials depending upon the height above the ground. At about 1 kilometer distance from lightning, let us say peak vertical field is 2 kV per meter. Then you can see that if height is h, then you get if it is 1 meter distance, then you get 2 kV voltage, this floating voltage. Now, if it is a perfectly conducting plane, there is only vertical field, but due to the poor conductivity of the soil, there will be a horizontal component for the field also, and that field is approximately 10% of the vertical field. So, if you have a cable that is being laid, so you have a voltage. So, this is your cable and this is your EH. So, if you travel certain distance, then the voltage that will be produced, the open circuit voltage that will be created will be this field times the length of the cable. So, around 200 volts per meter can be produced on the shield as an open circuit voltage due to this vertical field from lightning. Now, another property you have to be aware in lightning is that around 40% of flashes have more than one termination to ground. So, this can be within the same flash. So, it can be that one particular stroke has happened here, then after say several tenths of millisecond, the second stroke may follow partly the same channel, but then it can take a different termination. So, it is as if that lightning has struck one part of a building, then the second stroke may strike within few tenths of millisecond another part of the building. So, it is a very complex kind of environment, and the distance d is from 10 meter to several kilometer. So, sometimes even from the base of the channel you will see totally two separate channels to the ground. And another interesting phenomena is that around 30% of all flashes, the first stroke is not the biggest. So, usually the first stroke is the biggest, but in about 1/3 of the flashes perhaps the second stroke is larger than the first stroke, or the third stroke is larger than the first stroke, even though on average first stroke is the biggest. So, what happens at the point of lightning strike? So, one is the heating effect because of the large currents and temperature. So, melting of the metal skins, which is primarily proportional to the amount of charge that is involved, that is integral of the current over time, and temperature rise in wires or exploding wires. This is primarily proportional to the action integral, that is integral of I squared dt. So, it is as if that is a wire is subjected to that current, then depending upon the resistance of the wire will be heated up. So, this is the potential prospective energy that is available. Then potential rise of grounding. So, since there is large currents and voltages involved, the striking point will rise in potential, and this drives voltage and current surges along any connected system to the other systems. So, due to that there can be surface arcing along the ground, and you have danger of step potential and touch potential in connected system. We will describe what is meant by step potential and touch potential. First of all, the exploding wires due to impulse lightning type of currents. Because of the enormous energy inputted, the wires may explode. This is an experiment from a high voltage lab of wire exploding when you subject it to lightning type of currents. Often most of the reasons for fires during lightning strikes are this type of exploding wires. When it gets into electrical wiring, antenna, TV antenna wires, etc., it may explode and cause fires. And direct lightning strike to overhead conductor. Suppose, so this is a railway line. These lines may have surge impedance of the order of 400 ohms. Assume that your lightning has a peak current of 30 kiloampere, the average current. Then when it is striking the line, the prospective voltage would be 400 ohms times the current. Current times, impedance times the current. So, the current wave may be divided into two parts on both directions. So, we divide by 2. So, it can reach up to 6 million volt, but of course, it will not reach up to before that it will start flash over. So, you will never measure 6 million volt because it is already flashing over, and there will be current division between different conductor systems. So, lightning currents can get into here, it goes flashes over to the other wires, all over the place it will be going. Lightning surge in wires, the consequence. Even if 10% of a lightning current is in an earthing wire, let us say peak di by dt is 10% of 100 kiloampere per microsecond and inductance is 1 microhenry per meter, then the over voltage produced would be L di by dt. It will be around 10,000 volts per meter. So, suppose you have a lightning strike to even 10% of lightning current is carried by a big generator set or something like that, or outdoor equipment. In its earthing wire, it can have 10,000 volts per meter of the wire compared to the ground. So, earth potential rise at grounding rods. So, this can be even at the lightning grounding rod. So, which will tend to drive currents readily away from them to all connected systems. So, this phenomena can be illustrated by a simulation. So, typically in substations, power substations, we have substation mat in the form of a grid underneath the substation buried, so that the 50 hertz power supply, it is kind of a equipotential grid, so that you do not have any big potential difference between different parts of the substation under 50 hertz, even if there is large current flow through different wires. But is this enough during a lightning strike? But during a lightning strike, this will not remain at equipotential. That is shown here using a simulation. Soil resistivity is 100 ohms meter, or you can represent it as 1 by 100 ohm meter, or 0.01. So, this is equal to 0.01 Siemens per meter in conductivity. So, this is resistivity. So, this is conductivity. So, it is 1 over resistivity 1 by R, let us say. So, the current is injected to one corner, then you are measuring the voltages, transient voltages at various nodes. You can see that within the first 2 microseconds, you do not have any equipotential grid here. There are huge potential difference between various points. Only after that you reach a steady value, and when you reach a steady value, you can see that this is around 40 kV, around 40 kV. The whole grid goes up in potential to 40 kV, and that may drive currents to adjacent systems. So, now here more or less equipotential, but again it is at a higher potential level during lightning strike, and during this time you do not have any equipotential during the first couple of microseconds. So, this one has to be aware of. So, if you have one system connected here and another system connected here, then through the cable of the systems you can have very large currents following because of the potential difference between those 2 points during the first 2 microseconds. Lightning current on cable shields. We have seen the transfer impedance of cable shields before. Suppose 10% of lightning current is in a cable shield. The low frequency transfer impedance is, let us say, 10 milliohms, which is the DC resistance, and the leakage inductance, which indicate how much magnetic field will penetrate through the shield, let us say it is 2 nanohenry per meter. Then peak 10% of peak current and 10% of di by dt. So, even though we cannot add this part which is more or less resistive and this is inductive part, let us say approximately let us add that and see how much or voltage we get. So this is all together you get around, let us say, of the order of 50 volts per meter. So, as the current is traveling along the cable, even though it is 10% of lightning current, 50 volts open circuit voltage between the shield and the current will be produced. So, this is so here if you measure the voltage, so this voltage is almost equal to 50 volts per meter of this line. The step and touch potential due to lightning. One purpose of lightning protection is to reduce the step potential and the touch potential to those values that are not harmful for human beings. So, step potential is defined like this. So, if you have some horizontal current flow or if you have a horizontal electric field, it will drive some currents, and between the legs of a person it can create certain potential difference. So, the lightning protection system should be designed in such a way that this potential is not harmful for the person. Similarly, if the person is touching any part of the lightning conductor system, there is a potential difference between the hand and the feet, and this voltage called touch potential should not be above a value that is harmful to the person. So, this concludes regarding the properties, and next we will go into more on actual protection principles from lightning.